Welcome back to the same old video where we are going to learn about the multi-body simulation in Matlab with the help of Matlab on-ramp courses and some maths. So we are going to resume our course from 57%. Okay, so the topics we have to cover today, or you can say tonight, is assemble bodies, where the assemble multi-body system is first topic. The second topic is actuate multi-body system, and the third topic is model complex motions. So let's go to the simulation part and start the course.
Degrees of freedom, or DOF, are a fundamental
So
concept in.
if you are new to my video, then I will tell you that I already completed this portion, so I will move towards the next part, which is nothing but okay. So these are the different types of joints, 6 DOF joints, which allows the robot, or you can say which allows the model to move in 6 different directions, like x-axis, y-axis, and z-axis, and it can also rotate in that axis. Now the bearing joint, as the name suggests, it is like a bearing, so it will rotate. Okay, brushing joint, Christian's joint, constant velocity joint, cylindrical joint, gimbal joint. Gimbal joint is like gimbal camera, where the point, the higher point, or you can say there is a fixed point in a body which does not depend on any type of shocks which are going in the world, or you can say world frame. Now lead screw joints, and there are different types of joint we can find in the multi-body joint library. So what we have to do, joint features. Besides providing the required degree of freedom between bodies, joint also have other useful features, like internal spring for a dam force. Okay, since multi-body joints are ideal by default, they model ideas sorry they model ideal degree of freedom with no energy dissipation, and motion is only affected by the gravity. Okay, in the real world, however, things are less ideal. The mechanisms are exposed to frictions and other causes of energy dissipation, making it impossible to create the perpetual motion machine. That's why we can add the damping force coefficient and the spring stiffness and the equilibrium position coefficient here by manually typing the values. Next, now we will move towards the exercise. Okay, so what we have to do, we have to do some tasks, and based on that task we will gain some experience. That's the concept of this whole exercise. Now the task is, the parts are currently all rigidly connected. Okay, so the parts are rigidly connected means there is no movement in the simulations when we try to run this. Okay, so the model does not animate yet in the mechanical explorer, or you can say mechanics explorer. To allow the shoulder part to spin freely about its z-axis at the revolute joint, so we have to add here revolute joint. So we will add some revolute joint here to your model and connect it between the base and the shoulder. Like this. Next step, go to the dialog box of the revolute shoulder, and here's the dialog box. This is the dialog box, and in the z revolute primitive, which is this, go to the state target, click on specific velocity. No, we have to click on specific position target, where we have to define the degree of rotation, which is 90 degree, and an initial velocity target. Here is initial velocity target. This is the initial velocity target of 1 rev by second, means 1 revolutions by second. Leave the property to high desired for both the targets. Okay, with this we have completed this part. The next part is the revolute giant dialog box. Expand the sensing section. So in this we have to go to the sensing section and enable the velocity. After that, then use a PS simulation block. After this, we have to use the PS simulation block, which is nothing but it will convert the PS output to, sorry, it will take the output from skip multibody and it will show on the scope of simulation, or you can say simulink scope. Okay, submit. Next, expand the Z revolute permittive of RZ internal. Okay, so we have to go here and then we have to expand the, sorry, we have to expand the Z of the internal mechanics section, and then we have to write the specific damping force of 0.5 E minus 4, and it is set to newtons into meter per degree per second. The dimension is too much complex, but at the end, if the model is working, then it's fine. Yes, now you can see our mechanical hand is moving perfectly without any type of blockage. This is because we have used the revolute joint instead of the rigid body. Let's go to the next task where we have to allow the parasmatic joint a follower body. We have to add the parasmatic body, sorry, parasmatic joint. Then we have to add it between the base and the rail. So that we have to set some parameters here. Next, in the parasmatic joint, what we have to do, expand the limit section, then we have to select the upper limit, and we have to write some parameters, that is bound. So bound will set to minus 0.3, sorry, minus 0.3 meter specific lower limit and the upper limit. So the upper limit will set to 0.3 and the lower limit will set to minus 0.3. Okay, next, in the parasmatic joint dialog box, expand the z parasmatic primitives. Okay, go to the sensing part and right click on the upper limit force, add the required blocks and view the signal on the scope. PS and scope. Okay, you have to connect it directly like this, and then you have to connect it here. Next, open the dialog box of the parasmatic joint and expand the parasmatic primitive. After that, we have to go to the actuation parameter. This is actuation parameter, which is set to none. Change the setting to force it to automatically compute it, and after that we have to add the motion provided by input. Connect the PS sine wave block. Connect the PS sine wave block that is found in a foundation library physical sine wave source to the parasmatic joint P. PS sine wave block to the parasmatic body, and then we have to change the amplitude of the sine wave to 0.3 meters. And its frequency to 0.5 hertz. Okay, next, to measure the force required to generate the sinusoidal motion profile, enable the actuator force in the output of the sensing. Then make the necessary change to visualize the physical signal F on the scope block that you added in the previous task. I think I'm done the necessary changes there. Yes. So you can see right now, I can slide both my parasmatic joint as well as the hand joints. Okay, and the value you can identify in the scope is sorry. You can see the value is going linearly at 0 without having any type of friction here. Okay, so I have to add another block of scope, and then I have to connect that block into this part. Now we will run the simulation and let's check that what type of the difference we are getting in this scope, because at the first scope I can see the proper constant wave, but at this point I can see the wave start from 310. Let's assume 310 to 0, and then it's vary up to okay. So signal is much more confusing than I estimated it. Now the next part that we have to do, so we will complete this part or this course today, and for tomorrow we will go towards the proper CAN protocol, where I will understand the extended and the CAN CAN FD and CAN extra protocol in D with the help of Matlab. Now Delete the PS sine wave block currently attached to a charismatic block. We have to delete this block. Then open the charismatic dialog box. We have to open the charismatic dialog box, and in the actuation section, change the force parameter to provided by input. And the motion parameter to automatically computed. Next, expand the sensing section and enable the position. Connect the PS, which is this, PS converter to the charismatic joint F, which is this part, and the let's see, let's run the simulation to observe what are the changes that I have done from this. In the charismatic joint dialog box, expand the limit section and enable the checkbox specific. Okay, in the charismatic dialog box, expand the limit section, which is already expanded. And then we have to select both the section, then change the upper bound to minus. We have to change the upper bound to minus 28 centimeters, and lower bounds to 28 centimeter. Does the robot base still goes beyond the real limit? Sorry, I have done the opposite of what I have to do. I have to set the minus, and here I have to set 28. Now we will run the simulation and let's check. Okay, I think I have done correctly now. For the upper bound, it is set to 28 centimeter, and for the lower limit bound, yes, it is perfectly set. So let's click on submit. The next, I delete the constant block and replace it with the sine wave block. Sine wave block. Okay, not this block. Sine wave block. Then I have to set the amplitude to 50. After setting the amplitude to 50, add a scope block to monitor how the spinning and the damping force of the bound, sorry, uh, add a scope block to monitor how the springing and the damper force at the boundary stop the motion of the robot base on its track, resulting in a clipped sinusoidal motion. Connect the scope to the output of the PS converter just before the sum block. Okay. Scope. Just before the sum block. Okay, so I have to connect it just before the sum block. Am I right? So we have to use it here, I guess. Yes, that is perfectly done. And now my animation is running very smoothly, and I can also see the perfect sinusoidal wave in the constant bound I can see the perfect sinusoidal wave at the boundaries, and these waves are caused due to the damping and the springing force. Next session, joint primitives and degree of freedom. So these are some formulas for the degrees of freedom and joint primitives. That's some different types of joints, that is cylindrical, prismatic, revolute, and etc. Which joint can be used to model the full range of rotational motion of a shoulder in your body? Spherical joint. It is like the common sense, like the shoulder use a ball and socket joint, so we will use the spherical joint there. Which joint can be useful to model the motion of inserting, rotating, and moving to the moving a key to open a door? I don't know. I think the planar joint. Oh, the cylindrical. Yeah. But how can it? I don't know. Which joint can be used to model the motion of the ball in the tennis game? Motion of the ball 6D, because it has to go in all direction. That's why 6 degree of freedom. Now we will go towards the project, I guess. Let's check the course overview, and we have completed the model contact 466. We have already completed the model contact force. Now we have to complete only 24% more, and then we will go towards the project where we can make our own robot drawing arm, which is much more fascinating. Okay, so this is, you can see, this is much more complicated than you can ever imagine, but we'll try to work on this. Run the simulation first to observe how the robot arms currently move. Let's see. We need to go on top. So the problem is in the hand. Okay. To prevent the upper arm from pretending the shoulder, you can limit the rotational range of revolute joint Q2, which is this. We have to, what we have to do? Prevent, so we can limit the rotational range. For the rotational range, when I go to the rotational range, let's see. Okay, so we have to go to the limits, and then we have to go to the specific lower limit, which is this, and we can set here minus 195, minus 1, sorry, 195 degree. Then test the model by setting an initial position target. So I have already said this. Actuation, no. We have to go to the state target and initial position now. So we have to go to this, and then we have to add the initial position, which is minus 120 degree. Let's check the simulations. Does this prevent the joint from? Yes. Now the shoulder is working perfectly fine, but the other part of the hand is like the pendulum. So we have to make sure that it will behave like a proper hand. For we have to set the upper limit of Q2. 20 degree. 20 degree. Then run the simulation with an initial position of minus 75 degree. Let's check the simulation. It has to be work. It's okay but not fine. Am I right? So for this, what we have to do to model the contact force between the robot wrist and the real component, follow this step. Add the spectacle contact force block to your model. Spectacle contact force to your model. Enable the, where should I place it? Okay. Robot wrist and rail component. So where is the rail component? This is the rail, the wrist. Okay, so what we have to do here, enable the convex hull port sensing. And how can I enable that? Convex. Okay. Where should I have to do that? Let's see the solution. Wrist and the rail. Okay. First of all, I have to connect it to the wrist. First of all, I have to enable the port name as convex hull. So let's go to the geometry part. In geometry, I have to go to the export part. In export, I will enable the convex hull port. Now I can connect this. I have to do same for the rail. Convex hull. That is perfectly fine. Now let's move toward the next part, which is nothing but the next session. With this, we have completed the model. Now we will move toward making our own project, which is nothing but a sketching machine. Let's start the course.
Moment into the world of robotics, and you'll soon encounter a powerful tool known as the robotic arm. Much like human arms, these versatile devices can lift and move objects with impressive dexterity. And the best part? No matter how long they work, robotic arms never tire or cramp, unlike human arms. They can work for extended periods, maintaining the same precision and consistency. Now, a unique kind of robotic arm is the robot drawing arm. Think of it as an artist, but with a stylus instead of a brush. This little artist converts a digital image into a series of precise movements, creating intricate and accurate drawings. With sensors monitoring every line and curve, you essentially have a flawless artist at your disposal. But these
Also, the
robot
drawing is
drawing arms
bad.
are not just artists. They're industrial workers too. In automotive factories, they apply precise coats of paint. And in the electronics field, they meticulously design and manufacture printed circuit boards with remarkable accuracy and consistency. So, are you ready for some hands-on experience?
Yes.
In this project, you'll put together your very own robot drawing arm, capable of sketching detailed drawings on a flat surface. You've already added prismatic and revolute joints for mobility, but you'll need to tweak the Simscape model to keep the stylus vertical and manage contact with a sheet of paper. Once you've got that down, you can set your robot artist free to sketch anything you like. Excited, are we? Well, let's get started.
Okay, so I will take the break for 5 minutes, and after that we will go towards the project part. Okay. Okay, so let's start. Now what we have to do, to model the thin sheet of paper, use an infinite plane block from on the search quick menu, sorry. Infinite plane. This is the infinite plane. This block model a flat surface for contact modeling. First add the block to your model. Yep. After that, then assign the value to 0.5. So the width will be 0.5 and the height will be 0.8 in meters. Okay. Now finally connect the block to the world frame. Okay. Connect the block to the world frame. Leave the geometry board G unconnected for now. You can also change the diffusion color. Properties, diffusion colors. Let's go to the paper and I will go to the white plot. Okay. Next. Submit. Let's run the simulation and check whether it is working perfectly fine or what changes did I have made by adding the infinite plane. Okay, so the sheet of paper is perfectly looking like a sheet of paper, but our joint is not perfectly working. And for that, what we have to do, add a point block to your model and connect it to the port R. Point block to the model and connect its the stylus tip. So we'll add this block here. Okay, then in the box dialog, change the size pixel to 4. You can also adjust the setting in the visual properties. We go towards the reddish part. Okay, well, it can be visible, that's why. Once you are ready, add a spectacle sorry add a spectial contact contact force to this and that. This no. Once you're ready, add the sexual contact block to your model and connect the sheet of paper infinite plane and the boiled point together using the geometry port G. Okay, so we have to use this control R. Now submit. Still not perfect. Let's see the solution. Okay, so the F part will come here and the B part will go there. Alright, let's see. Yep. But first we will run the simulation to check what we have done. It's not rigid body there. That's why the arm is going down and down. Since the stylus is a rigid attached to the wrist, it can also rotate along with it. You can add the joint that remove all rotation degrees of freedom, leaving only the translation along the three-axis structure. This joint is called Kardashian joint. Go to the world frame. F4 to the stylus tip. Now it is perfectly fine, but it's not writing. What we need is to make the proper robot which can write. In Kardashian dialog box, expand the selected section. In this dialog box, expand the selected composite force. Where is composite force? I can't see okay, this is the composite force and torque sensing. Then enable the constraint torque. Measure a new port TC. Sorry, a new port TC will appear on the joint blocks, which outputs a physical signal. So PS PS simulation converter. Since you are only interested in the construction, talk about the y directional. Use the selector block to only output the second. Let's see the solution. Selector. Use a selector block to only one output. How can I say the output ports? Okay. Okay. Add one to your model, and in the box dialog, make sure the input port size parameter is set to 3, input port size parameter is set to 3, and specifically a value of 2 for the index parameter. 2. 2. Once it is done, connect the output of the selector block to the scope. Everything is working perfectly fine, and I'm very much tired. Okay, so next thing we have to do is just reach the specific end effector location. For that, this we need to give the value for every axis of each joint. Next thing what we have to do, the engineer at Matlab. Okay. Navigate to the robot subsystem. Note that all 5 robot joints are configured to expand the position signal which they receive from the signal editor block. What we have to do here? Okay, this is the signal editor block. I have to connect each block to the port. Okay. So it will give the proper PWM signal to each motor. Oof. Sorry. Now you can see it is drawing something. It is drawing a simulation. So basically, I'm. Oof. Sorry. Next thing with this. we have completed the project. The last thing we have to do here is the next section, I guess. Yes, the next section. With this, we have created our own stylus making project, and it is too good, if you ask me. It is so cute to watch a robotic arm that you have simulated is doing the work. It's worth watching once more. If it is properly drawing, the simulation is perfect, and my hard work is paying off. It is so much cool to watch your own project working in a best way when you don't know about anything of multi-body simulations, etc. With this, we have completed our full course. No, I don't want to start any new course right now. Sorry, I don't want to give any type of feedback right now. With this, I have completed my course. Let's take the best thing that is typically needed for validations. All right. Sorry, mention of my project. Although I can extract that part and add in my simulations, but it will not fair. That's why I'm not trying to. Why can't I? Right. Okay. Certificate number 31. How proud. It's the progress report where I have learned about the introduction, multi-body simulation concept, model builds, position and oriented body, assemble bodies, model context force, and robot drawing arm simulation. 31. So what will I do? I will take that part in a simulation. I will take that SLX file, although the parameters are very much needed there, but we will think about. Sorry, we will see about that later. This is the second part, but the final result that I have to do is next part. This is the final result that I have to do. I will save it. Save as not multi-body simulation. I will save it as arm. This whole thing is perfectly saved. Now what I have to do, I have to go to this part, then I will go to my drive. You can see I can use ThinkSpeak also because it is technically free for me. There is the ARM XLS file. This is the ARM XLS file. This is 21. Okay, so I will take this file and I will download this file. I will save this file in specifically in my project. create the new project here. Moving on, and that I will save this FLX file. Yeah. With this, I have completed the multi-body simulation on ramp, and then I have to go to the next course that I'm looking for, which is circuit simulation on ramp. But we will complete this course in a next video. Till then, bye bye, be safe, good night.